now we've come to lab on fluid flow in pipes, losses, and flow metering. The two subjects are not identical. They come from the same basic physics, but they are implemented in different ways. And so we're going to try to outline how that happens. Let's start with Bernoullis equation. And Bernoullis equation is something that you should have seen in your fluid mechanics lecture course. It's one of the basic equations of fluid mechanics. And it goes like this. I'm not going to go through a derivation of this. I try to avoid derivations in a lab course. Make sure. I like to do this to keep my notation coverage, as my slow mechanics and foundation student will tell you. I have a bad habit, or maybe we'll make this u squared is equal to a constant. Basically, the Bernoullis equation can be envisioned in a number of ways, but basically it is an energy transfer statement for fluid in a single streamline from point A to point B, or point 1 to point 2. And so for piping flows, it's ideal to use. However, Bernoullis equation also assumes that the flow is inviscid, and since it's inviscid, that there would be no frictional losses. Well, we're going to find out, A, that that's not true for pipe flow, and B, we're also going to find out that there are cute little workarounds we can use to get around this problem, even by using Bernoullis equation. Okay, let's look at this thing. And I have a handout. I say handout, it's actually a web page on this subject. And basically going through all of the assumptions. The assumptions, first of all, being we're going to ignore the gravity term to start with. We're going to assume that the flow is incompressible. This is more of a general form of it. We're going to assume the flow is incompressible. You can have compressible flows. And in fact, when I was involved in my family business, we actually commissioned a study on a valve to determine its losses with compressible fluid, in that case compressed air, but we also ran steam through those valves as well. So if I make those two assumptions, and you can see the derivation in my handout, you end up with this. And this is from state 1. Oops, I made one. No, I haven't, not yet. Now, mechanical engineers in general prefer to deal in densities, while civils, particularly those in geotechs, look at unit weights. And the reason for that is density is useful. We're useful in dynamic situations, whereas unit weights is better off in static situations. And as I've mentioned, civil engineers tend to panic when confronted with things that move. But that notwithstanding, if I were to divide through by G sub C, this is what I get. And instead of rho, we have the unit weight of the fluid. That's useful because, if you remember from the pitot tube, we can actually estimate. This is actually units of head. These are all in units of length, and that head is we can see in the manometers, which work using the same principle as the pitot tube. Okay, if we had no losses, if our flow is truly inviscid, and as I mentioned, inviscid flow only exists in computers, we would be at this point, we could. And if we had, say for example, if we had a change in, let's suppose we had something like this. And we're going to have something like this in just a second. This is A1, this is A2, and if it's round, it's equal to, the A1 is equal to pi d1 squared over 4, and that's pi d2 squared over 4. About that. Whoops, that's A2. If I have a constant flow, the velocity of u1 to u2 will increase, and the equation tells me the pressure will drop if I measure a pressure difference. The problem is that Bernoullis equation breaks down a little bit because it doesn't take into account losses due to turbulence and flow losses, shear losses due to the viscosity and all that. So what do? Well, at this point, we start pulling rabbits out of the hat. And the first rabbit we're going to pull out of the hat is this one. On this equation, we're going to put a head loss term, some kind of head loss term into it, so that we acknowledge the fact that even though Bernoullis equation tells us that it's supposed to be, we know that it is. So we have a head loss term. Now if I take that and I do some rearranging, and I mentioned, I kind of glossed through it, Q is equal to constant. Unless you've got a leak, you've always got to watch for that in the lab. Q is constant, so therefore, and let's also assume that we're going to use the average velocity concept. And the average velocity concept says that the velocity, we know it's not going to be the same. The velocity, there's a lot of little charts. It's going to be something like this. It's going to be 0. Boundary layer theory tells us it's going to be 0 on the wall, and it's going to increase in the middle. But we're going to forget about that. We're just going to say it's an average. That Q is equal to VA, which is equal to U1, well, I'm sorry, I keep getting this. U1 A1 is equal to U2 A2. Now, if I put that in and I do a little bit more massaging, and I do a lot of rearranging of this Bernoullis equation, this is what's going to happen to me. Get this page turned. Some of you say, well, why doesn't he use the pink Android for his notes? Probably should. In any event, if I do all this rearranging and a lot of this algebra, which I already assumed it across the floor, I will end up with something like this. It is equal to A2 times 2 G sub C times delta H, which is the head difference between here, okay, minus the head loss. Now, those are two different quantities. We measure this. We have to figure out a way of guessing this. Times 1 minus A2 over A1. There. Now we have an interesting situation. If I can measure delta H, and I will measure delta H. I know A2, I know D2, I know A1 to D1. I can have a flow. If I know the flow, if I have some kind of reference flow meter to take the flow, which we'll use, it's not the greatest, but it'll get the job done. If I do that, I go through all of this, I will end up with this. The trout in the mill is this right here. I don't have, I've snuck this in, I don't have a good way of estimating that, at least not directly. If, however, I'm going to do, this is the big rabbit of the hat for flow metering. I'm going to take this out and I'm going to replace it with this. This is the coefficient discharge. Traditionally, it's defined as the actual area flow versus the effective area flow, or actually the way around, effective over actual. It varies from 0 to 1. Therefore, if you get 1 in your results, you have done something bad. So, which means you need to fix something. But in any event, this right here is what we have in terms of the A2 with A2 CD times this. We can actually determine, if we experimentally determine the coefficient discharge for a certain configuration, we can then determine the flow through there, because we can measure that, we know these, we know that, we can actually measure the flow. And that, in a nutshell, is how we use the coefficient of discharge to use that device to predict flows. And I'm going to show you what they actually look like in just a little. We've explained the operation of flow meters, and we're going to see how that works in the lab. Now, however, we're going to turn to the flip side of that, which are minor losses. The existence of that HL assumes that there's some kind of loss in that flow meter. While we're measuring the flow, we actually use energy, which is true. Which is why, from an energy standpoint, if you've got the real estate to do it, you're better off using something like a high flow meter, high CD flow meter like a Venturi, as opposed to a low CD meter like the Orifice. So and there are other trade-offs you have in design. However, these conclude with minor losses. Well, what is a minor loss? Minor losses are I don't know why they call them that. I really don't. And the reason why is that someone who's been in the industry as long as I have, and has dealt with as many hydraulic and pneumatic piping systems as I have, I can assure you that minor losses with poor design and poor configuration can turn into major losses in a hurry. And I've seen this happen. So, but before we start figuring out how to get rid of the minor losses, we have to explain what they are. Minor losses take place when we have either valves in the system, we have elbows, T's, other restrictions in the line that, changes in diameter, for example. It can, if we go from a large diameter to a small diameter, we can have a lot, and we can do it the opposite, small to large. We can have the same thing. How do we estimate those? Well, this is where the theory of this is the same as the theory of the other one. I'm going to start here. I'm going to get rid of all of this stuff. Maybe I'll just leave that there for a minute and see what we can, whoops, yeah, that's right. And if I start with this, and I rearrange it, and again, I'm going to avoid in the video going through, kind of like the washing machine deal, I'm going to avoid going through a lot of the algebra. If I rearrange this thing, what I'll end up with is the following. The head loss, or delta H, the head change, not head loss, the head change in the system from point 1 to point 2. And usually with devices, the head change, instead of being here, it'll be over here. In other words, the head change from 1 to 2. In the envisaged ideal world, if we didn't have any losses, flow continuity, the velocity is going to be the same. We should have no head losses at all. But we know in delta, we'll have no head losses and we'll have no delta H. But that's not true. If I rearrange this, I will end up with this. This equation. No. Square root is gone. There's no square root. In other words, if I knew the coefficient of discharge of this device, I could do the head law. In other words, I could do the delta. I could determine the delta H, which I know kind of from this. I'm using the delta H to determine the coefficient of discharge in the first part of the experiment, where I actually run a known flow through and made delta H. I determined CD by solving for this since the Q is known. In this case, delta H can be determined from the velocity and the coefficient of discharge. However, the problem with this formulation is frequently that we'll know A1 well enough. What we may not know is A2. If you've got a valve, for example, we're going to see this with the gate valve, where that area varies, or whether it's not really round, or whether we really don't know what that configuration is and really would rather not take a lot of time finding it out or putting a port inside of it. We can then reduce this equation if we take this term out. We reduce this down to delta H is equal to K U1 squared over 2 GCC. Now, in saying this, there are a few important things that we can use this for a variety of configurations. So basically, K and CD have a lot in common. They both are measures of head loss to a great degree. K can be as high as it is. You know, it's not restricted from 0 to 1 like the coefficient of discharge is. It can be much higher than that. So if you get very high results, that's according to Hoyle, let's put it that way. So therefore, we can use that if we can measure this quantity. We can definitely measure the inlet velocity. That's inlet U1 squared. We can measure the inlet velocity. GCC is a constant. And we can measure the delta H across the device. We can actually determine what our K is. And we can use that in the operation of the device and in the design of the device and its use in whatever system. Most valves and whatnot have a standard inlet port to them. If you're reducing down or going up to it, that's going to have some additional losses, and they can be put in series. One way of doing that, since I brought that up, we might as well go ahead and do it here, is the equivalent length. Not a subject that gets a lot of press in some fluid mechanics courses. We're going to do it anyway. If I've got a hydraulics, or a fluid flow system where I got a pipe, and then I have a valve, and then I have an increase in there, and then I've got an elbow, and then I maybe have a decrease. Maybe this thing's been kind of cobbled together and the flow goes through here. The use of for a straight pipe, and I'll just take this back. For a straight pipe, if we know the roughness of the wall or can estimate it reasonably, we can determine the losses in that pipe using the Moody charts or using equations that are based on the Moody charts. And these have been around a long time. However, what we can do is, instead of trying to cobble this thing together, say this is L1 of pipe. Let's say that we can I have an equivalent length. In other words, this turns into a length of pipe of this size, and this turns into a length of this size, and then this elbow turns into a pipe length. And as long as the equivalent lengths are referenced to one size of pipe, And things get a little trickier when we get into non-round conduits or pipes or whatever. As long as we can do that, we can actually just add all those up. And we can determine the equivalent length of a system. And if we determine the equivalent length of a system, it's fairly simple to use the Moody charts for the whole thing rather than to have to break it down. Losses down one element at a time. The equivalent length is D1 times the loss coefficient here over the friction factor. And I explain how to determine the friction factor. That comes from your Moody charts. You can determine it either with the Moody charts or with a formula. And I have in my handout that if, obviously not only just the, you have to know the roughness or be able to estimate the roughness of the pipes before you give an equivalent length to it. But this is a handy way of taking into account series losses in a fluid system. And I've used it in my practice, and I know other engineers have used it. It's not, you don't see it very often like you should, but one of the things that I do require is for the students to compute the equivalent length of the gate valve, which we use we use in the gate valve, equivalent to the pipe that's feeding it. And that pretty much covers the theory behind the fluid, between the flow metering devices and the quote-unquote minor losses, which your job as engineer may be sometimes to make sure they don't turn to major losses. So let's go to the lab and take a look at the apparatus we use to measure it, and then we'll get into the experiment itself. Before we get started, let's have a little tour of the apparatus. You see I'm panning on the flow bench. It's a fairly extensive apparatus and has quite a few experiments associated with it. The first thing I'm going to do is to give you a tour of the thing that we're not going to use, and that's the computer. The computer is currently not working, and we're going to use the Rotameter, which I'll get to in just a minute, to act as our reference flow. And it's not perfect, but it's served us well. Over here we have some of the thing at the very far right is one of the flow meters, electronic flow meters that we're not going to be using, and that's the reservoir. Virtually any hydraulic system, and it's not really a hydraulic system, but a system like this will have a reservoir for makeup water or whatever fluid is being run through. And then you see down there that, let me get a better shot of it, that blue thing is the pump, and the electrically driven pump, which actually pumps the water through the system. Over here is the control system. This can be operated either manually or it can be operated through the computer. Since the computer is not working, thankfully, it has a manual option, and we're going to use that today. The next thing is the gate valve. The gate valve is in the last part of the experiment. I'll come back to it. You'll notice that it is hooked up to a nice digital manometer, which I'm going to look at in just a minute. Notice also, and you need to watch these very carefully, I'll probably put these in whatever data set I use. The inlet diameter is noted on that little blue dimal label. That's a real dimal label. That's not one of these computer-generated fakes. So, as is the truth with all of them. We move on. This is the first orifice. An orifice is simply as you see from my notes, is simply a plate which actually just lowers the diameter through which the water, in this case water, it can be other fluids as well, pass. Now you'll notice that there are two ports in the orifice, one on the upstream and one just on the downstream. And those ports are connected to hoses that come around and come back to this, which is a manometer. This is a classic two-tube manometer. It has seen better days, and you would be reading this to take measurements. And in fact, you will be reading photos from it to take measurements on. All the way to the top. Okay. The next flow meter is your flow nozzle, and it's a little bit more sophisticated. It has some aerodynamicity to the transition, to the diameter transition, and so it's a little more efficient. Again, you have the your two tubes, and you have its manometer. Okay, moving right along, we have the Venturi. Notice that one of the big differences between a Venturi and the other is the fact it takes up more real estate. The Venturi has a much more gradual, throat down to its throat diameter, and as a result takes up more real estate. If you have the real estate, obviously a Venturi is more efficient. If you don't have the real estate, then you're obviously going to use something else. So that's a classic type of trade-off. And it has a very direct tubes to its manometer. And it has a manometer. Then we come around, you've got some elbows here. Another gate valve, and this is the rotameter. The rotameters go back to the early part of the 20th century, and basically as the flow increases, that float comes up and you read it off the top. I'm not sure if you can read that on the rotameter, but that's the way it's read. That's going to be our reference flow meter. And then we go past some of the electronic flow meters down this way as the water is coming back. And last but not least, we have the second orifice, which is right here, right before the flow returns back to the pump. And it also has its standard manometer attached to it. There's currently no flow going through the system. As I increase the flow, the rotameter reflects that. And what we do is we increase the flow to a point of the rotameter, and then we take measurements all out. I'm continuously increasing the flow out to show you how to actually increase it. You will also note that as I increase the flow, two things happen with the manometers. One, of course, is that both manometers begin to rise as the pressure increases, but also that the difference between the two likewise increases, which you would expect in the theory I presented earlier. This is the orifice number 2, and we're going to take it all the way up to full capacity to allow the constant capacity to resistance capacity and you can see that the difference increases as the flow increases. Okay, so what we're going to do here is I'm going to take a series of photos, and I'll probably put them on my own website with readings from all of these manometers. and the rotameter. And you can, once you see that, you can actually you can actually take the data and actually do the calculations which I asked for. We're going to start with the low flow and we're going to go up to maximum flow. And this is just the flow meter part. We'll get to the gate valve shortly. Now we're going to do the gate valve experiment. In the gate valve experiment, as you can see, we have a digital manometer, and it's ported on both this side and this side, right behind these two pressure gauges. And we're going to measure at different openings of this, we're going to measure the head loss across it. And we're going to compare that to the flow as I showed in the theory, and we're going to compute the K value. Now the inlet diameter of this is 1.48 inches. What I'm going to do is I'm going to run a quick demo of this. And the thing is that currently at quarter opening, I'm going to just increase the flow gradually. And as I increase the flow gradually, you can see that the digital manometer likewise increases the head. Now the head the digital manometer records is in inches of water. As you can see, the beauty of a digital manometer is you have a number of options. With the conventional manometers that we used in the other part of the experiment, we didn't have many options. We just had to measure inches of water or whatever it's graduated in, and that's it. We can do PSI and inches of mercury, which I try to avoid because the stuff's poisonous. And as you see, as I increase the flow, the watt will go up, which actually according to the theory, the value of, if K is constant, then the loss will, the head drop will vary with the square of the velocity going in. And as you can see, we can get considerable head loss at just a quarter opening. We're going to open this thing at a quarter, a half, and 3/4 and full. And what I'm going to do is I'm going to do something a little differently than I normally do. Because the fact the rotameter is across the room from me, I'm going to go ahead and let my video camera videotape the loss, whatever the rotameter is doing. And then I will take data points. So therefore, your data points are going to be a little arbitrary, as opposed to the nice fixed ones that we normally have in our report requirements. Don't let that phase you. I will tell you what opening we're at, and that's the way we'll do it. And then we'll just go to this data point, and this flow, and this flow, and this flow. You just read the flows right off the rotameter because that's what they're supposed to be. I know in class many times students will try to spend a lot of time, getting the so-called exact flow that's being called for, and that's nice in some applications. Here, however, what we're really interested in is not the exact flow we call for, but to know what the flow is and what kind of effect it's having, what kind of result it's getting out of the gate valve. So with that, we will proceed to go to our procedure. We will start with the quarter and we will go outward to the full opening. Now we're going to start, this is the valve is a quarter open, and we're going to survey this first data point, obviously, is the one we're at right now, and we're at rest. Now we're at the second data point. 0.6. There's 0.7. There's 0.8. There's 0.9. There's 0.10. And last but not least, there's 0.11. Now we will open the valve for the turn. We'll take data point. First data, we'll take data point 0, data point 1, 0 point. And we'll go again. This is for the 3/4 turn. First data point. Second data point. Third data point. Fourth data point. Fifth data point. Sixth data point. Seventh data point. Eighth data point. Ninth data point. And that's it. We'll stop again. Now we'll open the valve, turn it in, and we're at 3/4 of it. And the first data point we'll take will be obviously our initial point, 0 point. And data point 1. And data point 2. And data point 3. And data point 4. And data point 5. Data point 6. And data point 8. We'll call it data. with our initial data point. And we're off. First data point 1. Data point 2. Data point 3. And data point 4. And data point 5. And data point 6. Data point 7. And we're going to stop it. And that's it. Those are all of our data points. Now that we've taken the data for the gate valve, that concludes the experiment. Thanks for watching, and God bless.